Let's look at 8.1 example 3. So we're still looking at graphing y equals ax squared, but now we're going to see what happens when the a is less than 0, or in other words, when a is negative. So let's look at example 3. We're going to graph the function h of x equals negative 1/3 x squared, and then we're going to compare the graph to our parent function x squared. So our first step is we're going to make a table of values. So this time in their table of values, they went by threes. And the reason that they went by threes is because of this 1/3 right here. If it wasn't a fraction, then I would go by ones. I would start with 0, 0 in the middle, and I would go down -1, -2, up to 1, up to 2. But then I would have all decimals or fractions for my y's, which gets tricky to graph. So it makes it easier if you go by whatever the denominator is, or a number that's divisible by the denominator. It makes sense. So we're going to go by threes in the table. So I put 0 in the middle because that's where our vertex is going to be. And then I went down -3, -6, up to 3, up to 6. We're going to plug these x values into the equation. We're going to find out what they equal, and we're going to fill in the h of x values or the y values in the table. If I plug in -6 squared is positive 36 times -1/3 is -12. -3 squared is 9. 9 times -1/3 is -3. 0 squared is 0 times -1/3 is 0. 3 squared is 9. 9 times -1/3 is -3. And then 6 squared is 36 times -1/3 is -12. Next, we're going to plot these points on our coordinate plane. So look at this black graph here. This again is the parent function with just f of x equals x squared. Now we're going to plot the points for our new function from our table. So this is the point -6, -12. Here's the point -3, -3. Then 0, 0. Then 3, -3. Then 6, -12. And we're going to draw this smooth curve to form the parabola here. Notice how our parabola is now pointing down. The reason that this parabola is now pointing down is because this a value is negative. Another thing that we can also see is look at how much wider this graph is than the original graph. So not only did it point down, but it's also much wider, and that's because of this 1/3 here. Since 1/3 is a number that's smaller than 1, that's going to cause it to get wider, and it's called shrinking because I'm squishing this graph towards this x-axis, so it's a vertical shrink. So the graph does have the same vertex, 0, 0, and the same axis of symmetry, x equals 0. They're both right here. But the graph of h now opens down, which means that it's a reflection. Remember, when you reflect, you flip something over a line, which was going to be our x-axis here. So this was reflected to point down. It's also wider, so that means that the graph of h is a vertical shrink by a factor of 1/3, and it's a reflection in the x-axis of the graph of f. Let's look at another example, and let's listen to Big Ideas explain it.
Graph h of x equals -2/9 x squared. Compare the graph to the graph of f of x equals x squared. Begin with the graph of f of x equals x squared. Next, make a table of values. Substituting -6 for...
So I just want to point out, look at how they, again, went by threes in their table, because 3 is a number that's divisible by 9. Going by nines would be really big on our graph, so that's why they went by threes here.
For x and the function h gives h of x equals -8. Similarly, when x equals -3, h of x equals -2. When x equals 0, h of x equals 0. When x equals 3, h of x equals -2. And when x equals 6, h of x equals -8. Next, plot the ordered pairs -6, -8, -3, -2, 0, 0, 3, -2, and 6, -8. Then draw a smooth curve through the points. The graphs have the same vertex 0, 0 and the same axis of symmetry x equals 0, but the graph of h opens down and is wider than the graph of f. So the graph of h is a vertical shrink by a factor of 2/9 and a reflection in the x-axis of the graph of f.